So I want to welcome people back from another Earth to class, which we haven't had for a month. And it's spring.
Okay.
Want to welcome Chris Zappa back. Chris, where are you at Morningside Drive?
I'm on 113 in Broadway.
Okay. So we've had Chris several times and he does good stuff. So we're eager to hear what he wants to share with us this time. So Chris, take it away.
Take it away. Okay. All right. So this time I thought I always kind of start with a very similar beginning, but then I kind of delve off into other areas. So if you remember this, it'll be a good refresher. If you don't, it'll be hopefully interesting. The first part of it. And then I'll get into more details about some of the initial things I talk about. So let me move this over here. Share screen. Share this screen, right? This one. So enough, how many of you are familiar with this thing here? This is called Windy. So yeah, anyone chime in. This is interactive. I love people asking questions as we go. I don't wait. Um, but this is a tool. It's publicly accessible, windy.com. It's really useful for when we're at sea, or when we're trying to plan experiments, because it takes in the global models, the forecast models, weather forecast models, and assimilates it into this beautiful um, display. And I bring this up because I want to highlight couple things that are going to be topics throughout what I talk about today. But as I mentioned, this is a forecast model. And one of the, whoops, all right, that doesn't want me to, oh, no, no way. Okay, never mind. Oh, all right. So here's the model, but you can choose different models. ECMWF is a traditional classic model for weather forecasting, and I'll talk about that a bunch of times in this. But this is a map of the wind right now on the ocean, or over the globe. And you can see here's the US right in the middle here. Here's the North Atlantic, and you see up here, you see these really high wind speeds up here. This is around 20 meters per second up there. And you can also toggle to another um, property, which is waves. So this shows what the waves are looking like out in the ocean right now. And you see up here in the North Atlantic, there's 7 meter waves. These are huge. When a 7 meter wave is like 7 meters high, that's almost two stories or more of of a city building. Um, and down here, so my team is down here about to cross this area from Antarctica in the Ross Sea up to New Zealand here, and they're going to go through all this pretty rough seas down here. But this is kind of this right now is an observation, but if you move forward in time, this is the model. And my research is all about understanding the physics and the processes that go into describing the model. So I'm going to come back to some things where I'm trying to understand things that then go into these models. So I'll be talking about, when I mention ECMWF, think of this framework, this model. And if you're not familiar with Windy, I can send it to, or Michael can pass it along to you guys. So now I'm going to go to oh, no, not that one, this one right here. I think I just need to swap screen. Let's move. There we go. So now you see the presenter view, right? I mean the presentation, correct?
Yes.
Great. So I wanted to talk about, in general, atmosphere-ocean exchange and why do we care about waves? So how are waves implicit in everything we do between or try to understand in how the ocean and atmosphere exchange heat, exchange energy, exchange momentum. It's all intrinsic to what we want to understand. So I've already kind of highlighted that air-sea exchange processes control are a controlling factor for both global climate and regional weather, as I was showing earlier. And it's also important impacts for human life in terms of shipping, fisheries, coastal flooding, and military operations. Um, so some of the physics, physical properties, processes that we're trying to understand is, so when the wind blows on the ocean, it generates waves, and those waves eventually grow. They interact with the near surface ocean and they'll generate secondary flows like this, what's called lane recirculation, which is these vortices that are really large and do a lot of mixing. And then eventually waves break and they produce bubbles and turbulence and sea spray. Um, and all this is driven by the heat fluxes across the ocean and the atmosphere. Um, so the just for context, the upper 30 meters, other 30 feet of the ocean is roughly the same weight as the atmosphere above. And as I mentioned, bubbles created by breaking waves dissolve gases that are absorbed by the ocean. So one of the things that we study is to understand the carbon cycle. So over here on the left, this 9.6 is what is being put into the atmosphere. And then it's what's being put into the atmosphere. And then this 3.1 is what's being taken up by the land, vegetation, things like that. And then the ocean over here takes up about 3 gigatons of carbon. So 9.6 goes out, 3 gets absorbed by the land, and then about 3 gets absorbed by the ocean. And so that's roughly you're leaving behind about 5 gigatons of carbon in the atmosphere every year. So what one of the things I try to understand is what's driving this uptake by the ocean, and by understanding the processes, we can make predictions about if there will be more or less that will be taken up by the ocean in the future. So this is kind of a map of what carbon uptake looks like on globally. So in here near the equator, there's actually carbon going into the atmosphere. But in these regions in the mid and high latitudes, like that place where I showed you where the big waves up there in the North Atlantic, there's lots of carbon uptake. And down here in the southern hemisphere, where all those big waves were, there's a lot of carbon uptake. So you can see there's lots of variability in globally in the carbon uptake. And what we're really doing is, getting the net uptake by over all the ocean is really the difference between two very big numbers. So to understand the processes and what this flux map really looks like is important because we're taking a really large number and looking at the difference between um, all these little segments of uptake and outgassing from the ocean. So it's really important to get that number well prescribed. So one of the things I study is wave breaking, waves, and wave breaking occurs at high wind speeds. And these areas where there's large waves, you get lots of bubbles, and bubbles both absorb gases faster than without bubbles. And you can see here, this is a cruise I was on. You can see there's lots of waves and lots of bubbles, lots of breaking. Now, so what we're trying to understand is how fast does the ocean, does that transfer occur across the ocean? So do I have it here? No. So the how fast the any gas is transferred across the ocean is has traditionally been looked at as a function of wind speed. So the faster, the higher the winds, the higher the transfer rate, the rate of transfer. But as you get to really higher wind speeds, when braking happens, there've been a lot of discrepancies in what that behavior looks like. So some people think it follows a linear with wind speed. Sometimes people think it could be quadratic, this u squared, and some people think it could be u cubed. And but again, this is wind speed is what they're using to parameterize it, but we know that waves are what are driving it. So by looking at these different, if you choose one of these different rates of transfer, so this is what seasonal CO2 fluxes look like if we looked at latitude as a function of latitude. So remember, we were looking at this map. It's if we averaged at every latitude what the flux is. So that's what we're showing here. So on the left would be uptake by the ocean, and on the right is outgassing. So the outgassing is that red area that I showed at the equator. And each of these curves is for a different relationship here, whether it's linear, quadratic, or cubic. So the linear case, you have this curve of uptake, and if you go to quadratic, you have more uptake at those regions, and cubic, you have the most uptake, as you'd imagine. But which one of those is real? So you have you can't really constrain that number very well if we don't understand this relationship of the rate of transfer with wind speed. So we wanted to come up with something different. We know that wind generates the waves and braking and bubbles are important. Um, so both braking is important both in terms of it generates turbulence, so mixing, and it also generates the bubbles, which absorb more gas. So, right. So what we did was we went out out to sea, made all those measurements of the gas transfer, this rate of transfer, and we also measured what the waves were doing. And here's a picture of what it's like out there. So this one we could be on deck. They allowed us to be on deck it wasn't too bad, but it gives a sense of a second here. You're going to look up when you're in a trough of a wave, and a big wave is going to come by, and I think the wave came on deck and pushed. This wasn't me taking the picture, I don't think.
Let us know if you need Benadryl.
But where is it? It should be coming up here. And waves kind of just come out of nowhere sometimes, and there it is. You you had no idea it was coming, and you just kind of get sideswiped. But I really enjoy going to sea and being in these kind of conditions. So here's a little bit later in the storm up here in the upper left here. You can see how big the waves are getting. And this was a storm called the St. June Day storm. This was back in 2017. But so out over the ocean, we were out just nuts in the Labrador Sea, south of Greenland, and it was a big storm. And people over in Portugal, you can see this guy here. There were huge waves off Portugal, and which was made for great um, surfing. And you can see this guy right there surfing down this huge wave near Portugal. And here's the people thinking they're safe, watching from shore. But you can see it was just rough rough seas all up and down the northern European coast. So we go out, we measure waves, and here's that storm. You can see it's going to show up here in a second. This is a map of the waves. So there's that waves, that storm with the waves in it right there. Boom, is another one. So we go out and we measure the waves, and to try and remember collapse this relationship. So here's against wind speed, but if we consider the waves, we can model this rate of transfer with not just wind speed, but a wave related parameter. So wave height. And here you see it collapses all the data sets really nicely. So instead of using wind speed, now we can use this, we call it a wind wave Reynolds number that characterizes this rate of transfer a lot better and will help us constrain that number of CO2 uptake by the ocean. And right. So I want to now that's one little intro topic. I want to go in a little bit more detail about um, fluxes in general, heat fluxes, momentum fluxes, energy fluxes. So what drives everything in the Earth is solar radiation. And 80% of the solar radiation incident on the ocean surface is absorbed in the top 10 meters. So all that heat is just trapped right at the surface unless there's some way for it to get moved around. And I think everyone's familiar with the greenhouse effect. So things get absorbed by the earth or by the ocean. So the sun can come through the atmosphere, but then when it tries to go out at a different wavelength, it kind of gets trapped in the atmosphere. And all these gases enhance that trapping of the outgoing radiation. And it's, CO2 is one that we always hear about, but one of the most important is water vapor itself. Water vapor is a extremely important gas because it really does trap a lot of the heat and keeps our planet at a temperature that we can live. Um, but just to give an example of how much heat is absorbed in the ocean, this is heat absorbed by the atmosphere. This is how much it would require to um, melt the northern hemisphere sea ice. This is how much heat it would take to melt the mountain glaciers. This is how much it would take to melt the continental glaciers. This is what's absorbed by continents, and this is what's absorbed by the ocean. So heat is there's a most of the heat in the is absorbed in the oceans. Um, and also because all that heat is absorbed in the ocean, 90 to 96% of the primary production occurs right in the top 10 meters of the ocean. So, um, and primary production is the first link in the food chain. So 99% of the Earth living space is in the oceans. Now we did that. So now about in terms of our the fluxes and why we care about them and why waves are important. So as I mentioned, sun is the drives the um, the atmospheric engine. Um, so that pipeline, some gets reflected back out, and then a lot of that sun gets into the ocean. The ocean is like your fuel tank. Then you have exchanges between the ocean, so exchange of heat and exchange of moisture, that water vapor that we care about, and that gives warm, moist air. So that's your fuel, and then and that drives the engine, which is the wind, and then the wind generates waves and currents. And then there's that, and the waves and currents are kind of like the brakes. So what we're trying to understand is this schematic in this oval and everything we try to understand about that, what's going on in that oval, we feed into that ECMWF model later, or that weather forecast model. So all these scales of processes really occur at much smaller scales than those climate models and weather models can handle. So we're make parameterizations based on the physics that we understand. So I wanted to talk about surface waves, energy, momentum in the upper ocean. So we have the wind, it blows on the water. We'll get to waves later. But first, when you blow wind on the water, you um, you generate a shear at the surface, so a gradient in the velocity, and we call this the viscous stress. So the how much momentum gets from the atmosphere into the ocean right at the surface is all due to viscosity. And then away from the boundary, whoops. So that's the viscous sublayer that I was mentioning right at the surface. And then away from the boundary, we have what's called this log layer. And a lot of everything in the atmosphere and in the ocean has been revolves around looking at a log layer where we describe the the profile of the velocity by scaling parameters, both a velocity scale and a length scale. And the whole, whether it's the details of this aren't important, but what's important is that we use this friction velocity in the models and this roughness length in the models. So by understanding
Hmm.
how the structure of the of this profile of velocity in the ocean and in the atmosphere, we can better describe for the weather models. So a lot of this is just a plot of what people have done in the lab, and it's done extensively in the laboratory. But we haven't done a lot of this in the field, which is kind of the and the reason we haven't done it in the field is because waves really do complicate what we're trying to do. So it's no longer a flat surface. You have waves, and the waves change that profile of the velocity profile near the surface. So it changes how the transfer occurs across the surface. And we have wave breaking. Like I mentioned earlier, wave breaking for gas transfer was a big deal. But in general, wave breaking is really something difficult to measure. It's difficult to um, work into models. It's a very complicated process. And and the waves also generate what's this? It's called Stokes drift. So it's this kind of slowly migrating of particles in the direction of the waves. So what does the near surface profile look like when you have waves versus when there aren't any waves? So and understanding that is really important because that will drive the models. So what I want you to take away from this is on the left is people measuring what the velocity field looks like in the atmosphere. And then, so that's all the velocity over here. So this is just what is measured. And you try and break it down into different terms. So they try and break it down into a mean, and then a wavy part due to the waves, and then a part due to turbulence. So I'm going to talk mostly about the turbulent part. The wave part is very important, and I'll talk about that right at the end. And the mean part is the underlying what would be used in the model, and then we describe this wavy part and the turbulent part to feed into the models. And similarly, on the water side, the the structure of it's not this nice mean profile all the time. There's lots of eddies and that viscous layer is very thin, but right below that log layer that we talked about is really a log layer in the mean because there's all this structure of intermittent turbulence here, all these eddies that come down from the surface. And wave breaking itself, if this is the surface on the right here, and you have this wave breaking white capping, the pardon the sirens. The wave breaking kind of diffuses out as well. It spreads. It's not just in one, it's not less locally kind of diffuses out and that complicates it even more. So some of the ocean observing platforms that we use to look at these modulars, as I mentioned, in the lab, it's a lot easier than in the ocean. We use buoys and moorings here. I've used stable platforms like Flip since I was in grad school. We put out drifters and spars to measure. These are all things that measure near surface in the atmosphere or near surface in the upper ocean. Remotely operated surface vehicles from ships, obviously, we've done that forever. One really powerful tool is using offshore towers that are cabled and that allows us to actually do observations and science right from our office. So I can sit in my office, all my cameras and equipment are out here in the tower, and there's a cable that comes back to the shore, and all my computers are there, and I can just log in and start checking out all the data on it every day, on a daily basis, or my students. So this is kind of what traditionally oceanography has looked like. And more recently, there's a push to do a lot of ocean observation systems using autonomous and remote sensing platforms. And this idea of a super site where you have a lot of assets looking at a specific problem, where you have all the ones I showed earlier, all of these things there, but also have automated profilers and gliders and um, autonomous subs, all making measurements in addition to all the traditional ships and buoys and satellites. So there's a number of whole new types of remote measurements using gliders and surface vehicles, this wave glider here and this sail drone. People may have heard about sail drone. And then using UAVs. And the beauty of all these is that they can all work together in concert to really look at a problem nicely. I'll just show a quick, you may have seen this last time, but I always love showing this. So this is our autonomous, one of our UAVs that's fully autonomous. And the beauty of it is that if you're on a ship, you can go out and send this out to look for something. And you can map out a region. Once you find that what you're looking for, you can bring the ship to where you want to sample everything and then put everything in the water and really focus on those measurements that you want to make. And then also the beauty of it is that it's fully autonomous, which makes it really nice. And we get the data real time back as well. So then we go out, we look for, as I was saying, we use the UAV to go out and do some reconnaissance, looking around the ship. Everything, all the data comes back to our little headquarters here on the ship. And we find what we're looking for, like this really important, this patch of cyanobacteria bloom, which is they're very narrow, but they extend for miles and miles. So once you find it, you can spend days and weeks just studying this patch, which is really important for even enhancing uptake of or the solar radiation absorption occurs even closer to the surface, which is important for how things mix. So here's a picture of the one we found. You can see this long sinewy bloom in two different locations. And we would never have found it unless we had the UAVs to go find it. So here's what the ocean color looks like. So the what the cyanobacteria picture looks like, and on the right is that thermal image of the same patch. And you can see that there are these fronts of warmer water um, and cool water kind of nestled together at these fronts, indicating some kind of mixing and overturning. But so another thing with all these new instruments and observations provides kind of a new realm of um, capabilities in terms of big data science. So with these new transformational measurement perspectives, we can do real-time mission control and tasking with storage, movement, analysis, and visualization of this data. But not only that, with machine learning needs a lot of data to do something. So with these new measurement platforms where we can get lots of data, we can feed that into machine learning um, modules and really kind of build next generation models that could feed into those models. But it still needs to be rooted in our understanding of the physics. So I just wanted to highlight that. And now I want to go a little bit more in detail about a couple things we're working on that are important to those models, and I'll talk specifically about them. The first one is, oh, so this is kind of a schematic of a simple schematic of our ocean surface that I'm going to come back to now. So away from the boundary up here, remember I talked about turbulence. So the free stream turbulence, the flux, the momentum in the atmosphere is fully carried by the turbulence. And as you approach the boundary, as you approach the ocean surface, more and more of the momentum goes into the waves and it goes into that viscous stress. So it either goes into generating waves or it goes directly into the viscous stress. And I'm going to talk about both of those and why they're important. So our current understanding of how waves grow, um, there's three ideas. One is there's small existing pressure patterns on the surface due to that turbulence, which resonate with the water and create small waves. And that's the Phillips theory. Then there's the Miles theory that waves grow enough to feed back to the atmospheric flow, creating a wave coherent circulation pattern. And this is really the popular one in terms of the ECMWF model. And then at very high wind speeds, flow can separate, and that's the wave breaking, and that causes extremely large intermittent pressure fluctuations. And that's the Jeffreys theory. So it's this combination of Phillips is really good in the initial phases, the Miles kind of in that transition for wave growth, and then at very high wind speeds, the Jeffreys theory. So all three kind of are important or provide different understandings that are important for those models. So who cares about wind over waves? So I keep coming back to this model, this ECMWF model. And essentially, they want to understand how much momentum gets into the ocean and how much gets into the waves. And they use a simple that roughness length that I mentioned in the log layer to understand or to prescribe how much momentum gets into the waves. Um, Similarly, they do the same thing for heat transfer. They want to understand how much heat gets into the ocean, or into and out of the ocean, because that's what drives these models, both the wind and the momentum, and the heat transfer, and then that feeds into the wave model as well. So, right. So at low wind speeds, they do a decent job, but as you would expect at the higher wind speeds, when waves are really important and it gets really lots of wave breaking, it makes it a lot harder. Um, there's a lot more scatter, and we don't know much because there's not a lot of observations. So a lot of the work right now that we're doing is to try and understand these higher wind speeds and how we can help improve these ECMWF models. And it'll help us, as I mentioned, the two different theories, ideas of Miles and Jeffries. Miles is more about wave age. So wave age is um, the ratio of the wind speed to how fast the waves are moving. So the phase speed of the waves and the wind speed. So think of it as when the wind is going really fast and the much faster than the waves, we say that's a young sea because the waves are still growing and they're still getting faster and faster. So, but the wind is faster. It's still faster than the waves. Versus an old sea is when the waves are really fully developed. They're going really fast and the wind is not really driving the waves. So it's much lower. So that's why wave age is important in terms of describing the transfer between the ocean and the atmosphere. And then wave slope, when, as I mentioned, at the really, really high wind speeds and really, really big waves, wave age isn't really useful tool anymore, and wave slope becomes much more important. So the slope of the waves, and the slope of the waves gives you some idea of when or how or the breaking, how much breaking there is in the ocean. And again, this is important at these high wind speeds. So I wanted to talk. Okay, so the first thing is how much time do you want me to talk about, Mike? I can.
You're doing fine.
Okay, I have a couple more things I wanted to touch on, and happy to answer tons of questions or no to whatever questions people have. Um, so I want to talk about three things. One about this this near surface current, and like I said, lots of measurements have been made in the laboratory, but we don't know much about the near surface ocean. So we've developed a technique where we use on the tower. We're out in that tower off of Martha's Vineyard that I talked about earlier, and I do a lot of imaging, um, and I use infrared cameras, and I use visible cameras, and specifically I use visible polarimetry. And polarimetry allows me to look at the polarized light coming from the ocean, and from that polarized light, I can measure the waves directly, the slope of the waves, and therefore the wave height directly. So I use the infrared camera and this visible polarimetry to measure the flow right near the surface in the top 10 centimeters of the ocean. So I build up, I'm showing you the result, but we can, um, from the infrared camera, the green one here, that's the viscous sublayer drift right at the surface. And then the blue triangles here are the surface current due to, or just measured from the Doppler shift of the waves, but it gives us the exact velocity below the surface. So from these two techniques, we can measure what the profile is of the current, and we can get an estimate of that friction velocity and that roughness length in the ocean. So this is a lot of details that we don't need to go through. But the end result is, and this is what the wave spectrum looks like, but this is the end result. So we take the thermal imaging, and that gives us kind of a surface drift. We use the waves, these fine scale waves, and look at their Doppler shift to get the current in the near surface. And that builds up our profile of the velocity in the near surface, the top 10 centimeters. Um, and from that, we can get fit. We measure the slope of that line, and that gives us that friction velocity or the momentum, how much momentum is now in the ocean that was transferred from the atmosphere. And we also get this Z naught, which is what that model really wants to scale their, you know, their rates of transfer in the model. And for what we found was that the actual stress in the ocean is more than the stress in the air side. So there's some actually it's the other way around. There's more stress in the air than there is in the ocean because there's some goes into the waves. Some momentum goes in the waves. So there's an and these are so those are the measurements that say there's more we need to adjust the relationships that are used in ECMWF. And this is one of the ways that they do it. They use this roughness length as a function of wind speed on the right here. In that, so there's two models. There's this early model here, which is from 4 years ago, and then there's this newer model here. But our measurements show that the original model works a lot better than the new model. So that's something that hopefully will get fed into the operational ECMWF model eventually. All right. So another thing, so that's something that we've just recently are about to publish, and but it has ramifications for these larger scale models. Here's another topic, which is the turbulence in the wave boundary layer. Um, and that's typically driven by it's a balance in the mixed layer. There's how much turbulence is produced, production, mechanical production, shear, that's shear. Um, and then buoyancy is just, when you have strong heat fluxes, um, there's instabilities because surface water may get cooler than the water below and you have overturning. And then those two are called um, production, buoyancy production and mechanical production. And then that's balanced by dissipation. So all those turbulent eddies dissipate the energy. And that's kind of the balance in the mixed layer. But what's important is how do waves impact this balance? So that's something that's really important in these models because not only do they want to understand the momentum and the energy, they need to understand how much of momentum or energy goes into the waves and how much goes into the mixed layer. So there's all these ideas of, there's a wave breaking layer, a wave affected surface layer, there's energy gets transported down, and then below that layer, you get more your law of the wall, shear production layer. So there's all these various layers of of breaking and wave affected layers that where the turbulence is kind of diffused down from the surface. And there's a lot of effort to still try and understand these processes. So that's our motivation is to understand that the turbulent processes and how that affects the wave modeling. So as a little schematic, we have shear flow on either side of the boundary. The blue line is a water surface. Um, and our balance is always the production and dissipation balance each other in both sides. But when you have waves, this changes. And what we observe is that in the atmosphere, the dissipation is less than you would expect. And in the ocean, it's more than you would expect. The actual dissipation, how much energy there actually is. And that's important because these, whatever happens in the waves that allows for more dissipation is directly related or relate to the wave model, which is this right here, this wave model. And it looks complicated, but it's not. This, the change in, this is the wave energy model. So over here, this change in wave energy, we can just assume that there is no change, so that goes away. And really, this term right here is just the wave, the wave propagation. So here's, if the waves are just propagating along at different, all their different scales of waves, that is balanced by three source terms. This nonlinear source term is just waves interacting and as they propagate. But the two important ones are this input from the atmosphere, so how much energy gets input, and then how much energy is dissipated. And this is think of this as by the waves. So what I've talked about over here on up above and below is in the atmosphere and the ocean, but this relationship is strictly about the waves at the interface. So you can basically assume that this advection of the waves and the nonlinear transfer, they balance out. They're kind of the same magnitude. So the balance is really between the input from the wind into the waves and the dissipation of of energy by breaking waves, or by wave breaking. So how do we achieve this balance? So that's what we made measurements that showed we saw the deficit, we saw this excess enhancement, same tower, same measurements. Um, and we looked at how there's a how waves break. And I'm going to show, so we characterize how fast the waves are breaking and how big they are. So this is a really low wind speed case. The waves are really small, but just demonstrates that we can track these waves. But those are white caps. There's another important waves that are, and we call them microscale breaking waves. So these are waves that break. Technically, they break, but they don't have any entrainment of air, so you don't see them visually like you saw here. Like you see these white caps, we don't see in the background here, there's micro breaking going on everywhere, all over the place. And this is an example of what micro breaking looks like in a laboratory. So this is a thermal camera, and you see these scalloped disruptions of that thermal boundary layer, of the thermal boundary layer, that have a wavy feature to them. So that's the micro breaking. But if you looked at the visible picture, so you have this bore-like crest of the waves, and it disrupts that surface, which is cooler than the water below because there's a heat flux going out. So as you disrupt it, you see that warmer water come back up to the surface. Um, and so here on the right here, you see on the lower right, these are images of the waves themselves, and you see these crests, but they don't see any white cap, no bubbles. But you definitely see this patch of warmer water that coincides with that. And we call that microbreaking. So that's what this imagery looks like on the left. So if we characterize that breaking, the distribution of breaking of whitecaps looks like this, but all that microbreaking is all up here. So, and we need to capture all of this full spectrum of of breaking to then get at what that dissipation of energy is. So this is characterizing the breaking crest, the breaking process over here on the right, the spectrum, both white capping and the micro breaking. And then when we sum all that up, we can get the dissipation. But one thing we need to learn about, or one thing we need to characterize, is this B, which is the breaking strength, which is what is the important parameter in the model. So what we did was we took all that, we measured the turbulence in the ocean, we measured all the braking, and we can then figure out what B is, what this braking strength is. And here is braking strength as a function of wave age. So we've now come up with a way that the ECMWF model can use this important parameter for braking and as a function of wave age. And remember, so wave age, this is young seas over here. This is when waves are really growing on the left, and these are old seas on the right, where um, braking strength is not as important anymore. We can also, this is what I was just showing earlier, we can look at the dissipation from the waves. That's what SDIS is. And we can look at the energy from just in the ocean. And you see that they match up, they align really well, except down here at these, actually this, yeah, these are our data. Yeah. No, this is previous data sets. And we're showing that we actually see a nice linear relationship. Whoops. And again, to go along with um, this and this shows the fraction of how much fraction of dissipation supported by braking. So you can see at young seas here, all the dissipation is forced by braking, as opposed to here the old seas, not much um, of the upper ocean dissipation, upper ocean turbulence is driven by braking. So again, this is another important aspect to feed into that wave model that goes into the ECMWF model. So that SDIS term. And then SN is the input from the wind. And here is that SN versus that dissipation. And they line up reasonably well, but there's still some overshoot here and undershoot here that we still really have to work to understand a little more. Yeah. So that's, and now understanding both that braking strength and that the this and the SN relationship with wind speed, with wave age are important things that can feed into that ECMWF model to improve their modeling. And then I just have one final thing I wanted to go talk about, which is looking at that viscous stress. And we have a new technique where I've talked about infrared cameras to measure that surface, right at the surface. If I use, we developed a technique where I use 3 cameras to get at 3 layers right near 3 depths right near the surface in the top 100 microns to get directly what this viscous stress is. And if we can get the viscous stress, and we know we can easily measure this free stream part up stress away from the surface, then we can know exactly how much momentum goes into the waves and how much goes into the viscous stress. So we'll know exactly what this partitioning is, which again is important for understanding how things are modeled. And I'll get to that quickly. So this is this idea that I'm going to talk about has been around for decades. This is back in 1970 was first idea came around. And the idea is that infrared radiation, when you're viewing the ocean surface and you're measuring the surface using an infrared camera, the absorption coefficient of at a particular wavelength of light varies. So you can choose different wave bands in your thermal camera to get at different depths of the near surface. And McAllister and McLeish back in 1970 said, oh, we can look at these 3 regimes and we can get 3 different depths and we could measure what the heat, what the thermal gradient is. I want to do something a little different where I want to measure these different depths, but I want to use it to get at the velocity field. So the same way that I was measuring the surface drift at one depth, we can measure the surface drift at all three depths, and we can measure that viscous stress directly because we have three depths, we have three velocities, and we can fit directly to get the momentum flux, the viscous stress. So we built three different cameras, worked with the company to target the ranges that we wanted to. We went down to a wind tunnel in Miami, hit the three cameras. It's a pretty big wind tunnel. This is what the infrared camera, this is what the thermal imaging looks like. Here's it 4 meters per second, 7 meters per second, 11 meters per second wind. I've already shown you the one on the right here. That's the micro braking. You can see micro braking in the middle here a little bit. And on the left, you don't see any micro braking. You just see that surface drifting. But again, there's three cameras looking at each of these. At each wind speed, there's three cameras, and it's measuring three different depths. So we got the velocity at each depth that we can calculate this year to estimate the viscous tangential stress. So this is the red measurements are this new camera system. The green are the standard with the gold standard of particle image velocimetry in the same tank. And then all the gray ones are previous estimates. So we're right in the wheelhouse of what everyone's measured before and during our own experiment. And similarly, here's the next year where we tested it again and we did a lot more wind speeds. Again, it matches what was done before. And here, the green one is actually the stress that we measure on the air side versus here's the viscous stress. So the difference between these two tells us exactly how much how much energy or momentum goes into the waves. So that's the end goal of this. And then the real end goal is to say, okay, how much at all these different wind speeds, how much momentum goes into the waves and how much goes into this viscous stress. So this is what typical models say. They say that up here, this is the total stress and it's that's the viscous stress. So there's lots of viscous stress early, and then the wave stress kind of increases with wind speed. So we can feed these ideas into the new ECMWF model. Now that was in the laboratory. The next step is to go take that camera system, go back to the tower, do the same measurements we did before, but now have this estimate of viscous stress, and we'll really be able to come up with some new parameterizations for this ECMWF model. And I think I will stop there.
Thank you, Chris. Very interesting. Back during World War II,
Yes.
there was a tremendous amount of studies of waves in preparation for landing on D-Day.
Yep.
And you don't have a D-Day coming up, I hope.
Hope not.
Okay. So in the American Meteorological Society Project Ocean, we talked about deep water waves and shallow water waves.
Yes.
Most of your work seems to be deep water waves, right?
Yes. Correct. I actually have let's see. So I actually have a little, I was prepared for these. I have a whole little, so you're talking about deep water versus shallow water waves.
Right.
So just a quick notional idea or how to think about it. For deep water, you describe deep water waves by their wavelength. So a deep water wave is um, the depth is greater than half the wavelength. So typically, the deep water waves you can think of just that. that the depth is um, greater than half the wavelength. That describes a deep water wave. A shallow water wave is more like the depth is less than um, L over 20, the wavelength over 20. So that defines a shallow water wave. So most of the waves that I deal with are shallow water waves. I mean, deep water waves. The important thing about that is that a a shallow water wave, because the depth is it's shallow, the depth of the water depth is what defines how fast the wave travels, as opposed to for deep water waves, gravity and surface tension define how fast the waves propagate. I could have a whole separate a whole separate Earth to class on water waves on the one of my
Okay,
class
we'll consider that sometime.
if we'll see if you want to. I don't know, that could be I'd have to work really hard to make that more exciting. I did want to say one thing about deep water and shallow water waves, but oh, right. Do I have it here? No. But so think of one thing that I always like to point out are tsunamis. So tsunamis are typically generated well offshore, um, and either from a subterranean subocean landslide or some kind of a plate snapping. I mean, plate tectonics. Some seismic event. And tsunamis are usually generated in the deep ocean, and they're extremely long. The wavelengths are enormous. They're, kilometers long. So you could have a tsunami generated, and you think it's in deep water, but it actually is probably it becomes very quickly in shallow water. And a tsunami you can think of it as it's a fast tide because it's not hours long, but it's also not like what you think of when you see the ocean waves that I showed you in that video. There, you don't see them because the wave heights are only a few centimeters, maybe less, until they become up on the shelf here. Until they propagate up onto the shelf, you really don't even know they're there. And then when they do get to the shelf, it's more of a fast rising tide than looking like a wave, a classic ocean wave. And that's why they describe tsunamis as um, kind of a surge that lasts for maybe an hour and then it comes back up, or a half hour and then it kind of subsides. But yeah, that's the deep water and shallow water.
Okay, other questions?
If in the beginning there was a diagram about uptake of CO2.
Yep.
It occurs more in the northern latitudes. This temperature of the water has something to do with that?
Um, a little, some, but I would definitely say, I mean, if you look at that, I'll just bring this over here. I mean, if you look at this is the North Atlantic, here's the North Atlantic right here, right? There's Greenland. Now, if I go to the windy map, this is like right now. There's Greenland. There's the North Atlantic. I mean, those are the waves. And the waves right now are like 7.5 meters. So there's lots of breaking going on. And that's why you have that strong uptake in that region. I mean, you can also almost look at this and say, there's that uptake. Here's another band of uptake here. That's right. That's this right here. And then all this down here below Australia and Africa and South America over here. That's all this right here. All this red, right? So all these areas where there's really large waves, um, you have lots of breaking, and that's where lots of the CO2 uptick is.
I
As
see.
opposed to here near the equator, where it's very calm. Um, Here's the equator, it's very calm, but that's where we have with this outgassing. occurs. And that's more of the outgassing here is more because it's um, low wind speed, low waves, but it's also there's more carbon in the ocean there than there is in the atmosphere.
Oh, I see.
Looking at that region, the question comes up to my mind,
Yeah.
are there differences between El Nino and La Nina
The in terms of what the
waves?
in terms of the waves,
How the waves behave?
that is interesting.
Write it down. You can do that for your next research.
I mean, not to there may be some seasonal effects, yes, maybe. In as much as it impacts the wind field, yes,
Yes.
yes. I mean, in the end, it's going to be driven by the wind more than anything. It's not going to be driven by the changes in temperature or anything or precipitation. It's really the waves are definitely coupled to the wind. But what makes understanding waves complicated is that the that coupling between the wind and the waves changes as the wind speed and the waves change, and the directionality. Directionality is so as the wind and the waves are aligned, things really make sense. But a lot of what as wind and waves misalign, things change rapidly, and that's where a lot of our research is going towards right now is looking at how wind and waves misalign, or what happens when they misalign, or how do they grow, how do they dissipate energy. All these things are really unknown.
Okay. Well, we have one person on here who's probably a little bit shy to ask a question. We have a high school student here.
Okay,
Just tell him it's okay to go back into the water next summer
it's
on
okay.
the Jersey Shore. Okay, Mike?
All right. Thank you.
Okay, Chris. Thank you very much for another exciting Earth to Class program.
All righty, thanks everyone for your attention.
Okay,
Thank you.
we'll be back in April, and then we
Yep.
have one more in May, and that's it for this year.
I
The one in
wanted
May is our 250th.
Excellent.